Welcome back. Today we climb another step on the ladder system, where physics, chemistry and biology connect, and understanding becomes faster. In this video, we examine a 2018 NHT chemistry question through a cross-disciplinary analytical framework, applying the three-ladder system to uncover the underlying structures that link fuel and ideal gas concepts across the sciences. When the bottle is opened, the internal pressure drops to standard atmospheric pressure. This sudden decrease in pressure drastically reduces the solubility of carbon dioxide, causing the dissolved carbon dioxide gas to rapidly escape from the solution. According to the mass-time graph, the initial mass of the system is 1375 g. As the gas escapes, the mass steadily declines until it reaches a constant mass of 1350 g, indicating that the system has reached a stable equilibrium and no further gas is being released. The mass of the escaped CO2 is calculated by finding the difference between the initial and final mass values. To determine the corresponding volume at standard laboratory conditions, SLC, where the molar volume, Vm of a gas, is 24.8 L per mole. Step 1. Calculate the amount in moles. Step 2. Calculate the volume. Hence, the correct option is A. The question asks for the enthalpy change, delta H, when glucose is oxidized during cellular respiration. Since the stoichiometric coefficient of glucose, C6H12O6, in the given thermochemical equation is 1, delta H corresponds directly to the heat energy change per mole of glucose. Given that 72.0 g of glucose releases a total of 1.126 times 10 to power of 3 kilojoules of energy, the molar enthalpy change can be determined through the following steps. Convert the mass of glucose to moles. Divide the given mass, 72.0 g, by the molar mass of glucose, 180.0 g per mole, to find the amount in moles. Calculate the energy released per mole. Divide the total energy released by the calculated number of moles. Assign the correct sign for delta H. Because the process releases energy, the reaction is exothermic, delta H less than 0. Therefore, a negative sign must be placed before the calculated value. Delta H equals 2.82 times 10 to power of 3 kilojoules per mole. Hence, the correct option is C. The key to solving this problem is recognizing that the fuel is a mixture of octane and ethanol, rather than a single pure substance. Therefore, the total heat energy produced must be calculated by determining the energy released by each individual component separately, and then summing them. 1. Energy released by the octane component. The mass of octane is equal to 91% of the total fuel mass, 2.50 kilograms. The energy released by octane is calculated by multiplying its mass by its specific heat of combustion, 47.9 kilojoules per g. 2. Energy released by the ethanol component. The mass of ethanol is equal to the remaining 9% of the total fuel mass. The energy released by ethanol is calculated by multiplying its mass by its specific heat of combustion, 29.6 kilojoules per g. 3. Total energy calculation and unit conversion. Finally, we sum the energy contributions from both components to find the total energy in kilojoules kJ. Convert the unit from kJ to megajoules mJ by dividing by 10 cubed. Cold weather can affect the performance of diesel fuels, such as petrodiesel and biodiesel. As the temperature is lowered, a point is reached at which the larger molecules in the fuel begin to solidify out of the liquid. When this point is reached, the fuel starts to become cloudy. The temperature at which this point is reached is known as the cloud point. The cloud point of a fuel is the temperature below which small solid crystals begin to form, giving the liquid a cloudy appearance. This property directly reflects the strength of the intermolecular forces operating between the fuel molecules. Fuels with weaker intermolecular attraction have a lower viscosity and a lower cloud point, meaning they remain completely liquid and continue to flow readily at colder temperatures. Structural and chemical comparison. Petrodiesel consists predominantly of non-polar alkanes. The only intermolecular forces present between these straight or branched chain hydrocarbons are relatively weak dispersion forces. As a result, petrodiesel requires much lower temperatures to solidify, giving it a low cloud point and superior flow properties in cold climates. Biodiesel consists of fatty acid methyl esters, FAME. The presence of polar ester functional groups introduces stronger dipole-dipole attractions in addition to dispersion forces. These stronger intermolecular forces allow the molecules to align and crystallize at higher temperatures, resulting in a high cloud point. Evaluating the options. A and B, incorrect. As biodiesel is characterized by a high cloud point due to its stronger polar ester groups. C, correct. Because a low cloud point is a feature of petrodiesel, enabling it to maintain an adequate flow rate in cold weather. D, incorrect. As petrodiesel has a low cloud point, and it contains a mixture of straight chain, branched, and cyclic hydrocarbons. Hence, the correct option is C. Co-escape and ideal gas mass loss from a pressurized drink gives moles of CO. Using SLC molar volume, the escaped gas volume was calculated as 14 L, M, CO, equals 1375, 1350 is equal to 25 G. Cellular respiration energy from 72 G glucose, total energy released was scaled to molar enthalpy, H equals minus 2.82 times 10 cubed kJ mole to the power of 1. Energy released per mole equals 1.126 times 10 cubed 0.400. Fuel combustion, octane ethanol mix. A fuel containing 91% octane and 9% ethanol produced 116 mJ when 2.50 kilograms was fully combusted. Cloud point of diesel fuels. Cloud point reflects intermolecular forces. Biodiesel, polar esters, has higher cloud point. Petrodiesel has lower cloud point and flows better in cold conditions. Correct statement: low cloud point petrodiesel, good cold weather flow. As we conclude today's lesson, remember that genuine progress arises from the strength of your thinking, from the clarity of the ladder of thinking you build, not from talent alone. The three-ladder system aligns physics, chemistry and biology into a coherent intellectual pathway, allowing each subject to reinforce the others and accelerating your understanding across the sciences. If you wish to continue developing this integrated approach, my contact details are available here.